Have you ever been in the countryside, away from the city lights, and looked up? Did you see that the night sky isn't all that dark? There's a feeling of contentness that's unlike anything ever before. The idea that maybe we're not alone out there, that there's stars and nebulas and planets. It's vast, but most certainly not empty. Welcome to today's video, where we're going to talk about what stars are and their life cycle. First off, what is a star? It's defined as a giant sphere of hot gas, mostly hydrogen, with a bit of helium as well. It is a self-luminous celestial body that emanates light through radiation and is held together by its own gravitational field. However, it can look different over time as it changes form and progresses through the stages of its life cycle. The life cycle of a star is composed of two sections, the generic and then the mass-dependent, low and high mass stars. A low mass star is defined as one with an area of 0.8 to 8 times our sun's mass, while a high mass star is one with 8 to 150 times the mass of our own sun. During the first stage, the star is a stellar nebula, also known as a giant gas cloud, which consists of dust clouds mainly composed of hydrogen. Gravitational attraction causes matter to accumulate in dense pockets that then collapse under their own weight over thousands of years. The temperature is low enough that the synthesis of molecules, which is the formation of compounds, can occur. As the gas molecules in the cloud collide during stage 2, heat energy is produced and forms a warm accumulation called protostar. Several can form within a nebula. As it gets smaller, it will spin more quickly due to the conservation of angular momentum, and the pressure increases, therefore increasing the temperature even further. During stage 3, the T-Tauri phase, additional molecules are no longer being attracted by the star. However, it begins to release a lot of energy. The core temperature isn't high enough to allow for nuclear fusion yet, and will not for about 100 million years more. Stage 4 is known as the main sequence star, when a fusion temperature of 15 million degrees Celsius is achieved, and hydrogen protons are converted into helium atoms in an exothermic reaction. More heat is released. There is stable nuclear fusion and radiation of X-rays. During stage 5, it can become either a red giant or supergiant, when all the hydrogen in the core has been used up and there is nothing left to be converted into helium. The star will collapse inwards, as there is no longer a force pushing it outwards from the center. After stage 5, the life cycle of a star is dependent on the mass. High mass stars, which have a mass of 8 to 150 times our sun, will then proceed with a fusion of heavier elements during stage 6. After there is no more hydrogen for fusion of helium, heavier elements are created, as helium fuses into carbon and oxygen, and carbon then fuses into neon and iron in the core. Neon then fuses into more oxygen and magnesium. Once iron is formed, fusion stops as iron will not provide a sufficient force to counteract the gravitational pull inwards. Stage 5 is the supernova state. Once there are no more reactions taking place within the core, the star will cool down and the pressure will suddenly decrease. Gravity will push it inwards, creating shock waves in the outer layers that will result in an explosion. It will leave behind a nebula. Stage 8 has two options. The first of the two is the creation of a black hole. As the core of the nebula continues to be an incredibly hot sphere, some stars will continue to be compacted and compressed into a small space. As so much matter is condensed into a small point of immense pressure, a singularity will form, and a black hole is born. Or, the supernova can become a neutron star, the densest stars, some of the most extreme objects in the universe. They rotate at incredible speeds and slow down over billions of years, and cool down as well. They are formed through a quantum mechanics phenomenon, as the matter is condensed into a very small point, but there isn't enough pressure to create a black hole. Then there are low-mass stars, which can measure between 0.8 to 8 times our sun. After becoming a red giant, they will become a white dwarf, After all fusion reactions cease, it will contract due to the gravitational pull, and the energy will decrease, resulting in it cooling down and fading to a white color. A supernova can form in a binary star system, where two stars orbit each other and are held together in their rotation by gravity, where at least one is a white dwarf. If the dwarf pulls in too much matter from the other star, or collides with the other, it can explode. And finally, there is stage 7, the black dwarf, a theoretical remnant of the white dwarf after it further cools down and no longer emits any energy or light. It takes quadrillions of years to form. Although we haven't been able to observe it, it is suspected to exist as the only fathomable end to low mass stars. Now, let's talk more about the creation of the elements, starting from the very beginning of it all. During the Big Bang, the universe was so hot and dense that protons and neutrons didn't form until a second later, which, for the time scales we're working with, was a lot. 3 minutes in, a lot of hydrogen, some helium, and trace amounts of lithium formed. Tens of millions of years later, stars formed as we've described, and more helium was created. Those stars then grew into giants and made carbon, nitrogen, oxygen, neon, and magnesium. The high mass stars created silicon and sulfur and other transition metals. Red giants and supergiants also released free neutrons, which, when absorbed by other nuclei, can form atoms all the way up to lead and bismuth. Then, during the supernova stage, more neutrons are absorbed and elements as heavy as uranium can be created. Meanwhile, neutron stars will create heavy elements like gold, mercury, and platinum during collisions. When cosmic rays hit some nuclei, they will break them down into lithium, beryllium, and boron. The heaviest and least stable elements are man-made in laboratories. And that's it for the life cycle of a star and a little bit about how they make all the elements we have in our world. Everything we see around us is technically made of star stuff, even ourselves. I think that's a pretty neat fact. Thank you so much for watching. Drop any recommendations in the form below and questions in the comments. I hope you've enjoyed enough to like and subscribe, and stay tuned for the next video. Have a wonderful day.